On this page of notes, we're now going to look in a little more detail at what happens when a dielectric is inserted between the plates of a capacitor. And we're going to follow two of Michael Faraday's classic experiments examining the effects of materials between the plates of a capacitor. Now we're going to start out here on the right with Faraday's experiment where he took a capacitor without a dielectric material between it, so just a vacuum between the plates of the capacitor, connected it to a battery, closed the switch, and fully charged the capacitor. He then inserted the dielectric material between the plates of the capacitor and observed what happened. And what he observed was that the charge on the plates increased. Now, the voltage did not change because the battery was left connected. So in case one, that's the battery remains connected case. The voltage remains the same because the battery is maintaining the voltage. And we understand that the charge increased because the polarization of the dielectric took the vacuum electric field, right? So that was the electric field from vacuum, and there was a polarization electric field when we inserted the dielectric now. So this is the electric field from the polarization, so that the net electric field, if we want to think of it that way, as E net equals the original electric field minus the polarization field. Now, we don't distinguish or measure the polarization fields. We only care about the E net. So when the net electric field is decreased, the voltage on the battery allows more charge to be pushed on. And when we plug in the result algebraically for our new charge, kappa times Q naught, so this was his experimental result. He saw it was directly proportional. The new charge was directly proportional to the kappa value, that you get kappa Q naught on V. Q naught on V is our original capacitance. So anytime we insert a dielectric, so this is one of the principal results we need to know without really any thought or analysis, anytime we put a material with a dielectric constant between the plates of a capacitor, we are increasing the capacitance by that amount. And this was one of Faraday's experiments to show that. Well, the other experiment that shows this, that Faraday did, was color-coded red over here, where, again, you start off with a battery with no material between the plates. You close the switch, as we did here, so we'll close the switch, charge up the capacitor, and then insert the material. But now, instead of leaving the switch closed, we disconnect it after it is charged, trapping the original charge. So the original charge cannot change, but what does change, we see, is the voltage. And what Faraday observed was that the voltage changes by this kappa factor as well. So you take the original voltage and divide it by kappa. And when we do our algebra, we see we get the same result because, of course, voltage and electric field go together. So when the dielectric material, now the blue would become the red, when the dielectric material reduces the net electric field by that negative electric field kappa amount, we get that voltage, right, equals ed. So when this is reduced, the voltage is also reduced, and Faraday saw it was reduced by this amount kappa. But again, the bottom line for us is to know that anytime the material is inserted, right, that the kappa will increase the capacitance relative to what the capacitance was with vacuum. So we're going to see a couple of applications of these experiments in circuits and how you'll make calculations utilizing these results. But as we have always done, pause the video, get your annotations down. If you have any questions, we definitely should discuss them in class before you go on to your applications.